Good morning, friends. I am Professor Sanjoy, Department of Geological Sciences, Jadavpur University, and today I will give you a talk on concept and classification of metamorphic facies and facies series, and an introduction to high temperature and high pressure metamorphism. But before going into the details of my topic, I would like to introduce the term metamorphism first. Metamorphism epitomizes solid state transformation of crustal rocks involving mineral content, mineral composition, microtexture or grain size under the influence of changing physicochemical condition that was prevailing at the time of their formation. Metamorphism actually encompasses the entire plethora of adjustment that rocks have to undertake in order to achieve a low temperature configuration when it is subjected to a very high temperature and high pressure condition. Now, what causes these changes? Temperature, pressure and fluid activity are the three major aspects of metamorphism, of which temperature is the most important one. Temperature, the effect of temperature on metamorphism can be manifested by four ways. It helps in developing the straight polygonal grain margin formation and giving the straight recrystallized mosaic texture. And secondly, the coalescence of the strain free subgrains at higher temperature to form bigger grains with high volume, low surface area. And thirdly, with increasing temperature, the thermodynamic parameters of the pre-metamorphic assemblages changed, and that leads to the destabilization of this assemblage and promotes metamorphic reactions. These metamorphic reactions are mostly devolatilization, and that leads to the drying up of the rock with increasing temperature and leads to stabilization of minerals which have less structural water or completely anhydrous. Now, the role of pressure in metamorphism. The pressure of metamorphism can be broadly classified into two types: the lithostatic pressure or the confining pressure, and the directive pressure or the deviatoric stress. Confining pressure or the lithostatic pressure is equal in all the directions, and it does not promote any deformation in the rock, and it can be calculated by the formula P litho is equal to H rho g, where H is the column thickness and rho is the density of the rock and g is the gravity due to acceleration. And deviatoric stress, on the other hand, is responsible for deformation, and it causes structures like formation of foliation, folding, tensional cracks like this. Now, when metamorphism starts, the metamorphism starts just beyond the milieu of diagenesis at very low temperature range, 150 plus minus 50 degrees centigrade, at a very low pressure condition that corresponds to 3 kilometer of depth. And while the higher temperature side of metamorphism coincides with the melting of the crustal rocks, and where we get formation of megmatites at the temperature range of 850 plus minus 50 degrees centigrade. The maximum pressure limit that metamorphism can record is in the range of 60 gigapascal or 100 gigapascal, corresponding to a depth of nearly 200 kilometer. Process like magma ponding at the base of the crust or inside the crust, or subduction of the lithosphere and collision of the continental plates, all these leads to the change in the pressure temperature condition of the crustal rocks. This time dependent interplay of the tectonics and the heat flow mechanism by the process of conduction, convection, advection or radioactive decay all leads to the perturbation of the steady state geotherm to a transient geotherm and trigger the metamorphism. Now, the metamorphism can be classified into two broad types. One is of local and another is of regional extent. Local metamorphism is always associated with the magmatic activity inside the crust, and the high temperature available during the cooling of this magma intrusive rock actually part of the surrounding thermal structure and causes metamorphism. The intensity of these metamorphic changes gradually diminishes with lowering of temperature difference with the intrusive rock and form a aureole, and this is known as the contact aureole of the rock. This contactorial rock don't need any deviatoric stress to form, and its texture is typically coarse grained, and it is known as the Hornfelsig texture. Regional metamorphism, on the other hand, as the term suggests, it is widely extended, and the most important regional metamorphism is the orogenic metamorphism, which actually occurred at the convergent plate margin, where compressional tectonics leads to formation of highly deformed metamorphic rocks with well developed foliation isocete like this. One of the major emphasis point of metamorphic study is to ascertain the peak PT condition of metamorphism and the transient geothermal gradient with a motto to evolve the idea of tectonothermal evolution of the crust, which actually undergoing the metamorphism. With this idea, the metamorphic petrologists try to solve the PT range of metamorphism during tectonism and gradually evolve the concept of metamorphic grades, the depth zone of metamorphism, the isograde classification of metamorphic zones, and finally zoom into the concept of metamorphic facies and facies series. Metamorphic grade is actually a imprecise relative term of to classify the relative intensity of metamorphic rocks. In this process, the metamorphic rocks of the area can be classified into very low grade, medium grade, high grade or very high grade, but there is no precise PT estimation. And during prograde metamorphism with increasing temperature, any low grade rocks can be transformed to a high grade one, or during retrogression the high grade rocks will transform to a low grade one. A better scheme of classification evolved when each metamorphic grade divided into different zones on the basis of first appearance of some minerals, which is known as the index mineral, and these index minerals actually identify the different zones. As for example, in this figure you show that it is the figure of the Dalradian complex of Scotland. Here scientist Barrow find the zonations from chloride zone to biotite zone, then the garnet zone, then staurolite, then kyanite, then sillimanite. And whenever one zone transgresses to other, it crosses the line which is known as the isograde, and isograde is nothing but the reaction line which is forming the typical index mineral. And this index mineral when forms through that reaction boundary intersects the plane of the mapping and form the isograde. Isogrades have some definite drawbacks as well. Isograde mapping is very much dependent upon the bulk composition of the rock as well. As for example, in normal pelites, the garnetine isograde appears at lower temperature compared to the andalusitine isograde, but if the bulk is high aluminous pelite, andalusite appears earlier compared to garnet because of the enhanced stability of the mineral. Secondly, in some rocks, particularly in calc-silicate rocks, the minerals or the isogrades are very much dependent upon the fluid composition. As for example, the ulastronite in isograde is dependent upon the reaction calcite plus quartz giving ulastronite plus carbon dioxide. In this reaction, if XCO2 partial pressure is more, then the ulastronite formation will be depressed and we will get more calcite plus quartz instead of ulastronite. Thirdly, most of the index minerals have a wide range of PT stability where they can stably coexist with other index minerals appearing earlier or late. So, all these processes suggested that a single mineral is not very conducive to ascertain the PT condition of metamorphism, and on this basis the metamorphic concept starts developing. Goldsmith in 1912, while working in the Oslo region of Norway, identified contrasting mineral assemblages stable in different bulk compositions. Eskola in Orjärvi region of Finland ascertained the views of Goldsmith and confirmed that there is a constant relationship between the bulk composition of the rock and the mineral chemistry. He also find that the Oslo rocks having Some of the Oslo rocks having similar compositions with that of the Oriyarvi rocks have different mineral compositions. As for example, the muscovite biotite assemblage of Oriyarvi rock is gradually transformed to chemically equivalent pair of cordierite and muscovite, cordierite and potash feldspar in the pelitic bulk, and he explained this as the effect of pressure and temperature, and he expressed this in a reaction as well, where muscovite plus quartz plus biotite is equal to cordierite plus potash feldspar plus H2O, and where cordierite plus potash feldspar stabilize at higher temperature side. On the basis of this, Escola confirmed that the rocks of the Oriyarvi region is metamorphosed at lower temperature condition compared to that of the Oslo region. And he evolved the idea of metamorphic facies, where he told that the metamorphic rock that has attained equilibrium at certain PT condition, its chemical composition is definitely controlled by the bulk composition. With pouring of new data regarding the stability of the minerals, Fife, Turner, Verheyen, all they are modified this metamorphic facies concept and give a new definition which shows metamorphic facies is a set of mineral assemblages repeatedly associated in space and time, so that there is a constant and therefore predictable relationship between the mineral composition and the bulk chemical composition of the rock. The corollary of this metamorphic facies definition is that rocks with identical bulk composition and identical mineral composition must be metamorphosed at identical PT condition, belong to same facies, whatever may be the space and age separation of these two rock types. Secondly, rocks of identical bulk when metamorphosed in different facies condition will definitely produce different mineral assemblages. And thirdly, rocks metamorphosed in same facies condition producing different bulk must be of different bulk chemistry. Metamorphic facies actually identifies the regular and predictable relationship between the bulk chemistry and the mineral composition of the rock, and there as a function of pressure and temperature. This metamorphic facies actually confirms the stabilization of different stable mineral assemblages at a certain PT condition, but fail to give the precise PT condition of metamorphism. And the boundary of this metamorphic facies actually marks the margin, marks the different metamorphic reactions, and these metamorphic reactions sometimes they are very continuous and not a precise line, and in PT space they are continuous over a range. On the basis of this, Escola and later workers classified the metamorphic rocks, metamorphic facies series into different types. Now, in this diagram, we will find that there are 7 facies for the regional metamorphism and 4 facies for the contact metamorphism. The 7 regional facies metamorphisms are the geolite facies, the prehnite pumpelite facies, the greenschist facies, the greenschist amphibolite transition zone, the amphibolite facies, the granulite facies, the blueschist facies and the eclogite facies. The greenschist amphibolite transition zone is actually not a facies, it is a sub-facies. So, it may not give a full facies category. The rocks of the facies of hornfelsig metamorphism includes albite epidote hornfels, hornblende hornfels, pyroxene hornfels and the sanitite facies. Now, from this figure it is quite clear that a very steep geothermal gradient where dTdP is nearly 55 degrees centigrade per kilometer is required for the development of these hornfelsig rocks, while an intermediate geothermal gradient, that is dTdP 25 to 30 degrees centigrade per kilometer is required for the development of facies like the greenschist, amphibolite, granulite like this. A shallow geothermal gradient with 15 degrees centigrade per kilometer produces rocks of eclogite and blueschist facies. Now, I will give the salient points of different facies first. Geolite facies actually developed in the ocean floor, where the igneous rocks, basaltic compositions, they transform to mineral assemblage like the geolite plus chlorite plus albite plus quartz with some clay minerals. Geolite is actually a mineral hydrated calcium aluminum silicate. The minerals like the wiereckite, the stilbite, the hewlandite, the lamontite, all these minerals stable at very low temperature condition around 200 degrees centigrade, just beyond the diagenesis, and these minerals doesn't need any deviatoric stress to form, as for example, these geolite facies rocks are completely devoid of any foliation. And since the geolites essentially contains calcium, geolite facies rocks are completely absent in the pelitic bulk, as the pelitic bulk is calcium poor. The stability of the geolites is somewhat dependent upon the XCO2 pressure. If XCO2 is more, then calcite plus clay minerals will stable instead of the geolite. Secondly, the prehnite pumpelite facies. It is another subgreen schist facies occurring at very low temperature, just beyond the geolite facies. Here the minerals like prehnite pumpelite will stabilize. Prehnite pumpelites are also hydrated calcium aluminum silicate, while in pumpelite we have FeMg along with the CaL. These minerals forms through the breakdown of geolites like the wiereckite, the lamontite, in the range of temperature 350 degrees centigrade at very low pressure around 2.5 kilobar. Next is the green schist facies. Green schist facies starts around 400 degrees centigrade, and the transgression from prehnite pumpelite to green schist facies is marked by the breakdown of prehnite pumpelite and the geolites, and leads to the stabilization of minerals like actinolite, chlorite, the epidote, the joycite, the calcite, the ilmenite, etc. In pelitic rock, which is actually a potassium rich, aluminum rich, calcium poor bulk, there we find minerals like calcite, minerals like muscovite, biotite, chlorite, along with some garnet, very manganese rich garnet. Otherwise, garnet will not appear. In calc-silicate rock, we will find formation of talc. And the name of this facies shows that the rocks must be green, and it is green because of the preponderance of minerals like actinolite, like chlorite, like epidote. All these minerals are green colored, and the formation of the actinolite is again dependent upon the XCO2 as well as the FeMg condition of the bulk. XCO2, when it is more, the actinolite formation will be suppressed and calcite and chlorite will be favored. On the other hand, if the bulk is more iron rich, actinolite will be favored. If the bulk is slightly magnesium rich, an amphibole which is known as the cummingtonite will appear instead of the actinolite. Now, the transition from green schist to amphibolite facies is through a transition zone, and this is not a pure metamorphic facies, it is a subfacies. And in this transition zone, the basic rocks particularly show a drastic change in composition of the plagioclase, where the plagioclase changes from albite to oligoclase. That means anorthite content changes from 3 to 18. This is known as the peristerite jump. The amphibole, which was actually actinolite initially, now changes to slightly aluminous one through some substitutions like the shenmachitic substitutions, the pergassitic substitutions, and chlorite getting diminished in composition becomes more magnesian, epidote also getting diminished in modal proportion and ultimately disappears. In pelitic bulk, the garnet, normal garnet, almandine pyrope garnet, it first takes its appearance. So, garnetine isograde at this transition zone. In calc-silicate bulk, tremolite appears in place of the talc. or tremolite talc coexist. Now, in the amphibolite phases is around 550 degrees centigrade, and here in the basic rock the plagioclase even more becomes anorthite rich, it becomes andesine, that means anorthite nearly 45, and more importantly the rock is essentially consists of plagioclase and amphibole. The rock name is amphibolite, and in pelitic bulk staurolite makes his appearance, that marks the initiation of amphibolite phases in pelitic bulk. In calcsilicate bulk, in the amphibolite phases, the mineral diopside appears. Now, from amphibolite phases to granulite phases, again there is a transition zone, and in this transition zone in basic rock we will find that clinopyroxene starts appearing, and along with hornblende plus plagioclase. Sometimes garnet may also appear, and this garnet forms to the breakdown of epidote. And in pelitic rock, the muscovite breaks down completely through the reaction muscovite plus quartz plus minus albite, giving rise to potash feldspar plus sillimanite plus water, and this is known as the orthoclase sillimanite isograde, and this is most important reaction in petrology because this marks the final demise of muscovite in pelitic bulk and first appearance of potash feldspar. And in granulite phases, when the pelitic rock and the basic rock, when they enter into the granulite phases, they starts to form typical anhydrous mineral assemblages, as granulite phases is the high temperature phases of the metamorphism. In pelitic rock, in granulite phases, we get stabilization of minerals like potash feldspar, sillimanite, spinel, cordierite, etc. In basic rock, orthopyroxene starts appearing along with clinopyroxene, and then plagioclase, then hornblende, all these are stable. So, this is actually the granulite phases condition is. Now, if we take the case of the very steep geothermal gradient phases like the albite epidote hornfels, hornblende hornfels, the pyroxene hornfels, they have the compositions very similar to the green schist phases, amphibolite phases, and the granulite phases. The sanidinite phases, which forms very rarely, very close to the igneous intrusive, consists of minerals like sanidine, which is the high temperature polymorph of potash feldspar. The shallow geothermal gradient actually leads to the phases blue schist and eclogite, and blue schist and eclogite phases, these phases are high pressure, low temperature, and high pressure moderate to high temperature phases. Blue schist phases marks the stabilization of minerals like jadeite, which forms through the breakdown of albite, the minerals like glaucophene. Glaucophene is a sodic amphibole, where the aluminum goes into the octahedral side instead of the tetrahedral side and enhances its stability. The minerals like leucionite, the aragonite, like this. In eclogite phases, which has a two part, one is high pressure, low moderate temperature, and one other is the high pressure, high temperature side. The high pressure moderate temperature eclogite will coexist along with some epidote leucionite, along with this glaucophene, some omphacetic pyroxene, and garnet. While you go to the high pressure, high temperature side of the eclogite phases, there the typical omphacetic pyroxene and pyrogarnet along with some kyanite stable. So, this is actually all about the salient points of the metamorphic phases. And now I come to the second part, that metamorphic phases series concept. Some of the metamorphic terrains of the world show characteristic variation in the peak PT condition in space and time, indicating progressive metamorphism along a particular line which is known as the metamorphic field gradient. That means, these terrains show a series of metamorphic phases assemblages developed from one side to other side. Maya Shiro, on the basis of this, developed the concept of metamorphic facies series, where he told that the characteristic facies that developed in this metamorphic terrains that showing the progressive metamorphism all depends upon the PT ratio of this metamorphic field gradient. He classified this metamorphic field gradient metamorphic facies series into three types. One is the low PT type, where andalusite at the low temperature and sillimanite at the high temperature stabilizes. This is also known as the andalusite sillimanite type. We also know that andalusite is the mineral that stabilizes at low pressure, and sillimanite is at the high pressure polymorph of Al2SiO5 that stabilizes at the high temperature. Example of this metamorphic facies series is Ryaku, the Abokoma and the Bushian. All these are low PT type. Here maximum temperature of 750 degree or 700 degree reaches within a very low pressure condition of 3.5 kilobar. Now, the medium PT metamorphic facies series, where kyanite stabilizes at low temperature and sillimanite stabilizes at higher temperature, and there we get temperature around 850 degrees centigrade at a pressure of 7.5 to 8.5 kilobar. And example is the Barrovian metamorphic sequence as observed in the Dallardian complex of Scotland. The high PT metamorphic facies series, where minerals like glaucophene and jadeite stable, and these are the minerals that stable at very high pressure condition, and example of this is Sambagua and San Francisco. Now, the last part of my topic is the introduction to high temperature and high pressure metamorphism. The high temperature and high pressure, the high temperature metamorphism is characterized by minerals that are typically anhydrous, that form through dehydration melting in facies conditions like the amphibolite granulite transition or the granulites or the higher temperature side of the granulite facies. In pellitic bulk, the amphibolite granulite transition zone, the first initiation of the melting starts at the fluid present melting, where muscovite breaks down to form the potash feldspar and sillimanite, and it is actually marks the formation of initiation of the migmatite. In the granulite facies, under fluid absent melting condition, the typical anhydrous minerals like spinel, like sapphirine, hypersine, cordierite, all these forms in rocks like khondalite, like lectinite, metamorphic granulite, all this. There is another part of granulite facies where temperature goes beyond 900 degrees centigrade, which is called the ultra high temperature of metamorphism, and this is very rare. And in this UHT part of granulite facies, there are some typical minerals stabilizes like sapphirine plus quartz association, which indicates temperature in the range of 1000 to 1050 degrees centigrade, and hypersine plus sillimanite plus quartz, that is also indicating 950 to 1000 degrees centigrade. Osmolite plus quartz, spinel plus quartz, all these indicates temperature very high, but this spinel must be poured in zinc. Now, the high pressure metamorphism part. High pressure metamorphism indicates the minerals that are formed through pressure dependent net transfer reactions having very low molar volume and higher molar density. The minerals like jadeite, the glaucophene, the omphacite, the garnet, pyrope garnet, the kyanite, etc. The metamorphic facies which actually have these minerals are blue schist facies, the eclogite facies, the high pressure side of the granulite facies, and the ultra high pressure side of the eclogite facies. In the blue schist facies and eclogite facies, the mineral assemblage I already have discussed. In the high pressure side of the granulite facies, the orthopyroxene will not be there, orthopyroxene will break down, while the UHT part of the eclogite facies will find that the quartz is not stable, and here the high pressure polymorph of quartz, the coesite is stable. Sometimes microdiamond is also stable. So, these are actually the regions of ultra high temperature of metamorphism. Now, to summarize the entire topic, it is found that the most important part of metamorphic petrology is to ascertain the PT condition of metamorphism, and here the single mineral will not do the job. The metamorphic phase is actually not a particular rock or a particular mineral, it is an assemblage of minerals that is stabilized within a certain range of PT condition, and that definitely indicates the temperature pressure condition of metamorphism attained during the tectonic processes. The metamorphic phases series concept is developing with time, and in regional metamorphism and the contact metamorphism that holds good. The phases series shows variation in the MFG, and that developed different phases mainly on the basis of the stability of minerals like Al2Si polymorphs, the jadeites, then the glaucophene, and we will find that the tectonism again played the important role in forming these geothermal gradients. And finally, this high temperature and high pressure metamorphic part, where we will find stabilization of minerals that form through partial melting or that form through typical pressure dependent net transfer reactions at specific metamorphic phases conditions. And these all part of my topic. Thank you very much for patient hearing.